Assalamualaikum and very good morning. We are from Group 5. Today we will present our project on corrosion analysis and control strategies for gas turbine system. My team consists of 5 members. Adam Daniel, Dani Sasongko Aji, Khalid Zakaria Atia, Muhammad Hafiz Ikram, and myself, Nur Zafitri. So each member is responsible for a specific chapter in this project to ensure a comprehensive corrosion assessment. I will begin with chapter 1, corrosion analysis. So, gas turbine operate under extreme conditions involving high temperature, cyclic loading, and chemical active environment. So, when ambient air entering the engine, it may contain moisture, sodium chloride, and sulfur compound, especially in marine or industrial environment. In the turbine hot section, so the temperature exceeds 800 degrees Celsius, promoting high temperature corrosion mechanism. Meanwhile, at the compressor section, experience low temperature but higher exposure to the moisture and salt deposit. Turbine hot section components are typically made from nickel-based superalloy due to the ability to retain strength at high temperature. Their corrosion resistance depends on protective oxide layer formed by chromium and aluminium. So in the compressor section, the stainless steel and titanium alloy are used. However, this protective layer can be damaged by the chloride exposure and thermal cycling. The dominant corrosion mechanism observed in the gas turbine system including hot corrosion, high temperature oxidation, and localized corrosion. The first one is hot corrosion. It is usually effect at the turbine hot section, component operating at 6 to 900 degrees Celsius. It causes by molten salt deposit, especially sodium sulfide, so which dissolve the protective oxide layer and expose the base metal to the rapid attack. This leads to the surface thinning and reduced load bearing capability. The second one is high temperature oxidation. It occurs when the alloy reacts with the oxygen at the temperature above 700 degrees Celsius. Although the protective oxide layer initially formed, but repeated thermal cycling during startup and shutdown causes cracking escalation, resulting in gradual material loss. The last one, in the compressor section, pitting and crevice corrosion are more dominant due to moisture and chloride contamination. So localized pit form when the passive layer breaks down, and this pit can act as a stress concentrator and increasing the risk of fatigue failure. Next, effect on performance. Corrosion results in progressive surface degradations including surface roughness, oxide gas spallation, and pit formations. So this defect reduces structural integrity by causing material thinning and increasing a likelihood of fatigue crack initiation. From an aerodynamic perspective, corrosion alters blade geometry and increases surface roughness, leading to the higher drag and reduces turbine and compressor efficiency. Operationally, this can lead in increased fuel consumption, higher vibration level, shortened component life, and more frequent maintenance requirement.
Assalamualaikum and good evening. My name is Adam Daniel bin Asrizal and I will be presenting chapter 2 where we conducted a root cause analysis of the corrosion. Now, our findings show that the damage isn't caused by just one thing. Instead, it is a synergetic interaction between the environment, the material used, and the stress of operation. So we have categorized these root causes into 3 main pillars: environmental, material, and operational factors. First, let's take a look at the environment. As shown in the picture of the turbine engine, the engine ingests contaminants like salt and sulfur through the intake. In the hot turbine section, these react to form what we call molten sulfates, which are the primary driver of hot corrosion. In the cooler compressor section, humidity allows these salts to form liquid electrolytes, so causing localized pitting or crevice. So essentially, the engine is constantly breathing in corrosive agents. So next, we analyze the material factors. Our turbine blades rely on thin protective oxide layer, specifically chromium and alumina, to survive. However, the root cause of failure here is fluxing. These molten salts we mentioned earlier actually dissolve these protective layers. So once that shield is gone, the underlying metal degrades rapidly. We also found that the material's own microstructure, like grain boundaries, can act as pathways for this corrosion to burrow deeper. So Finally, we have the operational stresses. Gas turbines are frequently started and stopped, as you can see from the picture of the thermal cycling. So this thermal cycling causes the metal and the oxide layer to expand at different rates. So this lead to spallation, where the protective layer simply cracks and flakes off. So when you combine this with a high mechanical vibration and centrifugal forces, any small cracks becomes a major initiation rate for corrosion. So that's all for me. Thank you so much.
The first proposed test is high temperature hot corrosion test, and the objective is to assess the susceptibility of turbine blade material and coating to hot corrosion under simulated subcontaminated high temperature environment. And the procedure is hot corrosion testing is typically conducted by depositing a control quantity of synthetic salt such as Na2SO4 or NaCl and Na2SO4 mixture onto the prepared specimen, followed by exposure to evaluated temperature approximately 700 to 900 Celsius in laboratory furnace. And for the remark, this method effectively reproduces the chemical reaction between molten salt and protective layer oxide, allowing for realistic evaluation of material and coating performance under turbine relevance condition. And for the second test is high temperature oscillation test, and the objective is to quantify the oscillation kinetic and oxide scale stability of turbine material during prolonged exposure to oxygen-rich environment. For the test and description procedure, specimen are exposed to controlled atmospheric condition at temperature representative of turbine service, typically 800 to 1100 Celsius. And for the remark, oxidation tests provide critical insight into long-term material stability and the durability of protective layers under realistic thermal loads. The third one is subspace for test compressor components, and the objective is to evaluate pitting and crevice corrosion resistant under chloride-rich humid condition. And the test description procedure, the subspray test is conducted in accordance with standardized method like ASTM B117, where specimen are exposed to a fine mist of sodium chloride solution at controlled temperature and humidity. For the remark, such spray testing provide a rapid and cost-effective method for screening material and coating against chloride-induced corrosion. Although it does not fully replicate service condition, it offers valuable comparative data for compressor environment where moisture and salt dominates corrosion behavior. And the last one is electrochemical corrosion testing. The objective is to quantify corrosion rates, preservation behavior, and localized corrosion susceptibility under controlled environmental condition. And the test description are electrochemical testing techniques such as potential dynamic polarization and electrochemical impedance spectroscopy (EIS) are conducted using a three electrode cell configuration. And for the remark is electrochemical technique offer quantitative repeatability and time-efficient assessment of corrosion behavior. They are particularly valuable for evaluating the effectiveness of coating and inhibitors prior to full-scale exposure testing.
When we talk about corrosion control in gas turbines, we are not dealing with a simple environment. These components face extremely high temperature, aggressive contaminants like sodium and sulfur, and continuous thermal cycling. So the key message here is simple. No single corrosion control method is enough. Traditional corrosion control often focuses on just materials or coatings. But in gas turbines, corrosion is driven by chemical, thermal, and mechanical factors acting together. So our philosophy is integration, which means combining protective coatings with AI and IR4 tools to move from reactive maintenance to predictive control. The most Critical corrosion control strategy in gas turbines is advanced coating systems. Nanostructures YSZ coatings act as the first line of defense, limiting oxygen diffusion and molten salt attack. Compared to conventional coatings, their refined microstructure significantly improves resistance to hot corrosion and oxidation, especially under thermal cycling. Designing coatings by trial and error is slow and expensive. By integrating AI with finite element modeling, we can predict coating performance before physical testing. Machine learning helps optimize coating thickness and composition, while reducing uncertainty, development time, and material waste. Cathodic protection cannot be applied to turbine hot sections, but it is extremely effective for supporting systems such as fuel tanks and pipelines. By integrating AI, the system dynamically adjusts protection levels and predicts anode consumption, avoiding under or overprotection. Traditional inhibitor dosing is usually time-based and inefficient. With IoT sensors and AI, inhibitor injection becomes adaptive, responding in real time to corrosion risks. This ensures effective protection while minimizing chemical usage and environmental impact. To conclude, corrosion control in gas turbines is no longer just about protection, it's about intelligence. By integrating advanced coatings, AI, and IR4 technologies, corrosion management becomes predictive, efficient, and sustainable. This is how modern engineering transforms corrosion from a problem into a controlled system.
Now I will present Chapter 5, which focuses on the corrosion monitoring plan. Traditional corrosion monitoring relies heavily on periodic inspections, which often detect damage only after significant degradation has occurred. To overcome this limitation, our study proposes a smart corrosion monitoring system based on Industry 4.0 concepts, integrating IoT sensors, AI, big data analytics, and digital twin technology. The main objective is to enable continuous real-time assessment of corrosion behavior and support. The monitoring system begins with an IoT-based sensor network designed to capture both environmental and material condition data related to corrosion. The sensors include electrochemical corrosion sensors to measure corrosion rate and potential, as well as environmental sensors for temperature, humidity, chloride concentration, pH, and conductivity. These parameters were selected based on the main root causes identified earlier, such as salt ingress, moisture condensation, and thermal cycling. Sensor placement is optimized at critical locations, including compressor inlet and casing, auxiliary systems such as fuel tanks and pipelines, and accessible turbine casing areas, ensuring representative data collection without affecting turbine operation. All sensor data is transmitted wirelessly to a centralized data platform, where it is stored within a big data architecture capable of handling high data volume and frequency. Artificial intelligence algorithms are then applied to analyze both historical and real-time data. The AI system performs a trend analysis to track corrosion progress, anomaly detection to identify sudden abnormal conditions, and predictive modeling to estimate the remaining useful life of the component. This allows early warning alerts, enabling timely maintenance decisions. To further enhance prediction capability, a digital twin of the gas turbine corrosion environment is the digital twin is a virtual model that continuously updates using real-time sensor data, material properties, coating characteristics, and corrosion kinetics obtained from laboratory testing. Using this model, long-term corrosion evolution can be simulated. The impact of operational changes can be evaluated, and mitigation strategies can be assessed before physical implementations. When abnormal corrosion behavior is detected, the system automatically issues early warnings, recommends inspection or maintenance actions, and adjusts inhibitor dosing or cathodic protection parameters. forming a closed-loop, adaptive decision framework. In conclusion, this study shows that corrosion in gas turbine systems is driven by combined effects of environmental contaminants, high operating temperatures, and cyclic operation. Because of this interaction, no single corrosion protection method is sufficient to ensure long-term reliability. Therefore, an integrated corrosion management approach was proposed, combining advanced protective coating, AI-assisted corrosion strategies, and smart monitoring system based on IoT, data analytics, and digital twin technology. The proposed system enables predictive maintenance, allowing corrosion to be detected and managed before critical damage occurs. Overall, this approach improves component reliability, operational safety, sustainability, while aligning corrosion management practices with Industry 4.0 principles. That's all from our group, and thank you for watching.